This video introduces the beta box, which is a graphical method of working with BJTs in order to do calculations of voltages and currents. It's built on the Ebers-Moll model of transistors, which graphically explains how the transistor circuit operates. In the PowerPoint, I'll be showing Kirchhoff's equation versus the beta box, and you can see straight away after that that the beta box is very nice to work with. So I think this picture here is one that you want to make pretty well indelible in your mind, because the collector circuit in the transistor, in the active region of the transistor operation, has no bearing at all on the collector current. All that collector current is controlled by this coloured in green area of the circuit, which I've called the control section of the transistor. So we have the base current and the emitter current working together there to set up a constant current in the collector part of the circuit. But of course, looking at this circuit, and if you've got a little bit of knowledge about transistors, this becomes a little bit difficult to do calculations, because we've got a voltage, a separate voltage in the base bias circuit, separate voltage in the collector circuit, and we've got a resistor here and we've got a resistor here. So it's not like where the emitter is just simply grounded. We've got two resistances here to work with in this circuit, and that becomes quite complicated to work out if you do it using just Kirchhoff's, but a lot easier to work out once you understand the beta box. Here's our beta box. Beta 319, base, emitter with the 0.7 volt barrier potential shown, and I've used a grey colour in the collector circuit because the collector circuit has no importance at all on the collector current when the transistor is operating in the active region. In the second video, I'll look at saturation and we'll see how we use the beta box there, and the fact that we have to do some alternate calculations for the collector circuit. So in here, what I've done, and this is the beauty of it, on the next slide we'll be seeing the some calculations, but on this slide 3, I've taken the 1 meg ohm base resistor and I've divided it by 319. And if you recall, we had 319 was the beta for the transistor. So dividing the base resistance by the beta of the transistor to give me 3135 ohms, and then being a complete loop here and working with the loop, I have to add this resistance to this resistance to get 5335 ohms, and then I can use the effective voltage, that is 15.3 minus 0.7, in conjunction with that new beta box derived value to give 2.74 milliamps, which is the emitter current. And then I can divide that by the beta of the transistor to get the base current for the transistor. And the base voltage for the transistor, of course, I would simply, what I've worked out here with the emitter voltage, add the 0.7 to it to take me back up to 6.72 volts at this point here. Let's have a look at the next slide and see what would be involved if we didn't use beta box. Around any closed loop, the sum of the voltages must be 0. Nice Kirchhoff equation. So remembering that we have this control loop, which is 1 meg ohm, 2.2 K, and we've got a circulating current around there called the base current. And well, this resistance here has two currents going through it. It has the base current and it also has the collector current. You might recall from basic transistor theory that IE is equal to IC. This is because the alpha of the transistor, which is the ratio between IC and IE, is usually about 0.99. So some years ago, most textbooks decided that they were as good as equal, so IE equals IC. Looking at an equation for this then, 0 volts is equal to 15.3 minus the 0.7 from the base emitter junction. Add IB times 1 megohm, that would be the voltage across that resistor there. Add IE times 2.2k, that would be the voltage across here. So these voltages have to all add up to 0. Pulling that equation apart then, I've done it in stages. 15.3 minus the 0.7, 14.6. And then what happens over here, I've got two variables on the first line of the equation. So that makes the equation very messy to work with. So I've put the second variable into an argument here, which is based on the IB. So that gives me two lots of IB in the equation. And beta of the transistor plus 1 times IB is going to be exactly what IE is. This comes back to that alpha, the old alpha equations that we used to use. Working through this, we get a IB of 8.57 microamps. On the previous slide, I had an IB of 8.59 microamps, so I'm only out by, like, what's that? 2/10 of a microamp. Not very much at all. Okay, moving on. Beta box, calculating the collector voltage. And once I know what IE is, again, just repeating myself, IE is equal to IC for all intents and purposes. So we can multiply the IE times the 1K here to get a voltage across the 1K resistor. And then I've got to minus that value from the 15 volts to get the 12.26 volts, which is the voltage on the collector. So you can see 2.74 volts is the voltage across that resistor based on that current flowing through it, being that IE is equal to IC for all intents and purposes. On the next slide, whoops, there we go. On the next slide, I've taken values from that have been computed by the simulator, and I've put them in here. 8.63 microamps, just a tiny departure. 2.75 milliamps versus 2.74, 2.76. So they're all within, well and truly within 1% of what I worked out. The actual graphical image that we'll be using in other videos shows the constant current part of the transistor, the beta of the transistor, and the diode junction, which has got the barrier potential of about 700 millivolts. This is iCircuit, a program called iCircuit for the Mac, and with iCircuit, it's a beautiful bit of software for doing quick development work and finding voltages. Like you can see, clicking here, it tells me I've got 2.76 milliamps, and between that point and ground, I've got 6.07 volts. With anything that we do in electronics, it's worth doing a laboratory for it. So a lab here based on the BC547 transistor. Just a picture of it there with the resistors around it. It also has a capacitor here across the emitter resistor, because I did some AC equations with this as well for one of the next videos. There's a larger picture of the lab, just with a wishboard and 3 milliamps, say, of collector current. 2.74, 2.76, that meter, you know, with the accuracy of the meter is showing around about 3 milliamps of collector current. the voltage between the from the base to ground, 0.667. Well, no, that's, sorry, I beg your pardon, that would be across the base, because here we have a emitter resistor. So 667 millivolts of base voltage in this device. Base emitter voltage, that would be base emitter. Yeah. Where did I get the original beta for the transistor from? I used a couple of transistor testers. I used the Atlas, which is quite reliable, got 315. I used this other newer device that I use for surface mount gear. I got 334. And also I did some curves on the transistor tracer, and I got about 319. So I said, well, we'll run with 319 as the beta. Okay, just in summary, it's been the first PowerPoint for the BetaBox series. Other PowerPoints will follow in the series. If simple base bias is utilised with no emitter resistor, no resistor equalisation is needed, which makes very, very simple to work out. If voltage divider bias is used, a Thevenin equivalent model needs to be made of that voltage divider in series with the emitter resistor. That'll be in the second video. All the slide content is original, and it's Creative Commons, share alike with attribution. Hope this was helpful. Thanks for watching.